It wasn't there?
Well, it's there, but it's the same recording that the first lecture. I think both, I don't know if you uploaded twice, because I opened the video and it was just the same recording as the previous one. But, you know.
Why did I do that? Check recording. All right. Thank you for letting me know. Check lecture 2 recording. I hope I didn't record over. Okay. All right. Well, do we have everybody in this? Yeah. Where is Anandu? Not coming? Okay.
I'm not sure. I'm going to be doing that. What is that?
Emily is not here. Sarah's not here. 20% out of their salaries. What's today's date? February. A big 20%. No kidding, not 2% to 20. What's today's date? The 5th. All right. So I have a question for you guys. To get us started, share with us a fun fact about any protein, any food matrix that has protein. Fun fact, anything, either fun or funny or any fact. All right, I'll give you a fun fact from me so that you know you can get inspired. All right, so that when I came to started work at the University of Minnesota about 18 years ago, I came from a postdoc position at Purdue, and at Purdue I was working with milk enzyme proteins, enzymes, native enzyme systems. So proteins, but only the enzymes and enzyme inhibitors. So when I came here, I wanted to do something different than what my supervisor was working on. So, and I know proteins since my master's degree, I worked with proteins. So the first protein research that I did was on soy protein. And at the time, I never had any food that had soy in it. So I didn't know that protein, I wasn't familiar with it. And I just said, oh, well, we're gonna start something new. And later on, I discovered, well, I don't like soy, but I discovered the texturized soy protein, like mimics chicken. So I realized if I get that and cook it the same way I cook chicken dish in an oven with lemon, garlic, and a lot of spices and potato, turned out actually good. Very good. So it's not the taste of chicken, it's the taste of the spices you put in there. Okay, so that's my story. All right, we gave you extra time to think. Tell us about something.
I worked towards like a gas fermentation protein. And it tasted very bad. It tasted like a media, so like very like musty, moldy.
Is that the air protein?
Yeah.
What do we call it air?
It's from air, it's like the microbes like takes elements of the air and then they ferment it into biomass.
So there are microbes involved. It's a fermentation. It's not like you take the nitrogen and carbon dioxide and oxygen and you make a protein. out of it.
No, and there's like, yeah, there's microbes involved and then the microbes kind of like produces biomass and then you still have to like purify that into like ingredient because you have to like kill the microbes.
And
So,
then what do? You just kill the microbes and extract the protein?
yeah, there's like downstream, I think it's been a while. I think like they kind of like explore either like membrane filtration or like pH kind of like isolation. And then that because like you have to have like a heat, heats like the kill stuff, like it just messes up the functionality. So they have a challenge there, but you need to do that to like, like be safer. But I tasted it, they can't get rid of like still the media flavor, so there's kind of like a carryover. Tastes really bad.
What about its nutrition?
Hmm?
The nutrition.
They seem like the PDCAS is still one.
The pedigree of one.
Yeah, so it has like the essential amino acids.
Hmm.
Yeah, I can show you. I don't know if they have paper, but I know like the name of the microbes.
Okay, and it's a patented process.
It is a patent, yeah.
Interesting. At first, when I first heard about air protein, you know what came to mind? Do you guys watch Star Trek? So you don't know the replicator. Who does? Nobody? What generation are you? Okay, so that won't make any sense. There is a replicator where they press a button and say what they want, and then it gives them the food. So it probably uses the air and other components. So like, oh, is that from Star Trek?
No, it's very challenging to learn. So it's not gonna get.
Okay, all right. So who wants to share a story about a protein? Yeah,
It's not a fun story. At that time, it was a sad story.
sad story. That's
Because,
acceptable.
We were making, when I used to work, we used to make the sports nutrition kind of products. Where we use different protein source and then fat source and then dry blend them and make the product. So we had a supplier for soy protein acid. And then there was during COVID, there was a lot of issues and stuff. And they were stopping getting those stuff from China. So we were trying to get other suppliers. First batch they will send us, then we will taste, we'll approve after analysis. Then they will give us the big batches, and then finally we will do it in pilot plant, and then it will be approved with all the everything. First it will always come good. Then the moment we will ask for 3 more lots for the same product, it will be always the worst.
Different.
Different. We
worse.
could never match with the original one. But
It's
it
a
was
trick the company
very,
gives you the very
so,
best.
yeah, the first time when we will say, then they will come with, oh, you already liked our product, so 3 batches are good. We will send you more, but give us the money or give us the PO for purchase order. Then we'll send you the bigger one. So it was like probably like one powder, we took probably 6 months to approve.
Oh,
It was
that's
a nightmare.
terrible.
It was a
Yeah,
nightmare.
to get a trustworthy supplier.
Especially like the extraction process and the treatments are so different for each company and they will not tell us anything and we have to go through all the analysis and then figure it out. It's
No, yeah, I feel it.
probably that's why I left the job and came for PhD.
Yes, that's a good choice. All right, any other? No, nothing you want to share, Cal? Okay, Cal.
During my internship with Purus, we were making a plant-based egg alternative. So to understand kind of like how an actual egg works, one day I put like egg white into a RVA, a rapid visco analyzer, and to kind of see like where it gels similar to the one that I was working on. And it was just pretty cool. It just like spun it up really fast and then just like gelled like
Instantaneously almost.
like really fast. Like I don't know what temperature like the egg protein gels at, but like yeah, it gelled really fast. And usually it would be like a paste kind of after with pea protein. With the egg protein, it was just like a puck, like hockey puck of
Wow.
of.
I thought the
gel.
story was you put it in the RVA and then you mix and it became all foam and everything came out of the mix.
Well, because it heats it too, so it literally just like spun it up really fast and then gelled, and then once it gelled, it just stayed as a pop. It's good.
Good. I like the theme, so you know what your work experience, who else has a work experience or internship that involved protein? No, your General Mills internship not involved protein? I'm so disappointed.
I work as a
Okay,
product development. I used to work in a like dietary supplement
Yeah.
company, and I used to do many like different tests with like whey proteins and sometimes I think they use pea protein too.
yeah.
Yeah, so I started liking protein there when I was there
That's after
testing
your-
new flavors. No, that was before my master's. Then after that, I joined master's.
Mm.
And actually, the proteins brought me here because I was researching bioactive peptides from beans and proteins, and I was reading articles, and I came up to your work.
That's good. So that's a very good story. You're quiet, but I'm gonna ask you, tell me something.
I'm searching.
You're searching? Okay, search. You work with rice protein. Tell us something miserable about rice protein.
Work with,
Huh?
is the worst part is work with rice protein. Yes,
It's the whole thing.
yeah. And the taste is really, really bad.
Rice protein tastes bad, why?
It looks like sand. It's the same taste, like sand or clay. Yeah.
Oh, so is it rice bran?
Mhm.
Oh, from the brand, not the actual. Okay,
So bad.
why did you do that?
Why not? I'm working with protein, so I need to see what I'm working, see
Okay,
if it's good or not.
so, okay. Well, in the middle, and fun story. No, I have a little problem. Okay. Maria, any fun story? No, not fun, miserable, bad experience.
But it's near 1 year that I faced with the protein. I never worked with that, never before.
Oh, that's a fun story. So this is the first year you work with it?
Time that I worked in the dairy
Uh,
and protein and everything is amazing for me. But the foaming, I think the foaming is related to protein. I always thought that it's right related to the fat.
So it's discovery.
Yeah.
Very good. What did you find for us? Nothing?
But I can tell something else.
Yes, tell us something else.
During my, uh, during my undergraduate program,
Yeah,
of course, we need to discuss around the selective food, and we choose plant-based protein products.
yeah.
And then I want to discuss more about the advantage of plant-based protein product.
Yeah.
I think maybe it costs less, but when I searched online, the results told me the most of case plant-based protein products cost more than the real meat.
Not as healthy, apparently. Yeah, I was, on Tuesday, I was meeting with a potential, like a foundation that might give gifts for plant-based research. So the first thing she told me before I started talking about Plant Protein Innovation Center, she said, don't tell me you're working on alternative meat. And I said, I'm not gonna tell you that because I'm not. So, and this is not what when I give a talk anywhere, I go, let's give plant protein their identity and not make them like meat or make them like cheese or anything. It's just, it's so sad when we try to change them into something that they're not. We're ending up with either more ingredient, more cost, more processing, adding a lot of fat and salt to make it taste better. But at the end of the day, it's not what the consumer is looking for.
It's not healthy at all.
No, because they're
In
adding,
the process.
yeah, they want to mask all the flavor that comes from pea or soy, and then they add a bunch of fat and a bunch of salt. And a lot of those ingredients that gives you the meat coloring. And then just like, what are we doing? Yeah, okay. Good. Let's now recap a little bit. Oh, Echo's here. Hi, Echo. How's Australia? You can tell us how's Australia.
It's good. It's hot and humid.
It's hot and humid, she said? Okay.
Yes.
All right. Well, no matter what, I'll envy you because it's cold, dry over here in Minnesota. Okay. Well, let's do some recap questions. What are some physical roles or technophysical roles of proteins? What do you remember? Anything physical you can think of. Yeah, so structure is physical, but also, functionality, okay, they contribute to functionality which can impact the texture of the food. But what other than that we talked about? Oh, color. So some gives you that white color like the casein, other gives you the natural red color like the talon. So, but what else colors might involve protein? Maillard reaction or enzymatic reaction might cause the browning. Sometimes it's desirable, sometimes it's not. Okay, so color and structural impact. Okay, that's fine. So what are some intrinsic factors that impact protein structure? Intrinsic factors. We haven't dived into a lot of it, but if you remember the map, so there is something internal to the protein and there's something external that might impact the structure.
Amino acid composition.
Amino acid composition, what else?
Sequence.
And sequence, very good, that's intrinsic. So that amino acid composition and sequence actually impact the other intrinsic characteristics, like the ionization state, functional groups, intermolecular interaction, conformation. So these are all intrinsic factors that are really impacted by the composition and the sequence. Okay, what are external factors? pH, temperature, salt, metals?
Yeah.
No, presence of, humidity, drying conditions, enzymatic modifications. So anything external related to processing that will potentially change the structure of your protein. And with that, functionality will be impacted. Can you give an example of how change of structure causes a particular change in a function? You can choose one structure and one function. If you pick solubility, change in pH. So sometimes the pH is close to the isoelectric point, the protein precipitates, you lose solubility. So because that pH impacted the ionizable group on the protein, and by changing that characteristic, we ended up changing a functionality. So we'll be talking a lot about structure of the protein and changes that will cause a change in the structure and how that will impact function. We will be doing a lot of that, and then we will focus on different types of protein, maybe egg, if we have time, since a lot of you like eggs. So what is the R group and how it may differ among different amino acids? Of course, I heard some of you started doing the Quizlets for amino acids to learn all of them. So I'm looking at you in the direction. Define the R group. What is R? If you have an amino acid, what is the R group?
Like the part that's around the carbon that's not the amino that's not.
Yes. Yeah. So the R group can actually be a hydrogen in case of glycine. Somebody has been studying. Okay, so yes. So the R group can be a hydrogen, but that's only for one amino acid. But then it will be different for the other amino acids, and it might carry a functional group, and it might impact interactions, formation of the structure of the protein, the configuration of the protein, and then the interaction of the environment. So that's very important. And we gave key examples on different amino acid and what interactions and reactions can happen. That's why studying the amino acids will make things easier as we go on in the class and talk about these structural and functional impacts.
And we can also call it side chain, right?
Side chain, yeah, you can say our group is a side chain, and it's different between different. Well, speaking of that, I just remembered we have an exercise on Canvas, a practice set. Did anybody see the practice set? It's under week 2. So you can print it out, work on it after we're done with this section, and then you can turn it in within 2 weeks and get a +5 extra. Okay. So again, this class is not about the grades, although somebody searched me before taking the class. And he's not even paying attention. So you search me on, what is it? Rate Your Professor. What is that website? This is to find out how many A's I give.
The gopher grades, right?
Is that how you found how many A's I give?
Sorry.
You found a rate of the class.
Rate of class? No, I cannot find the rate of class. I can just find the average grade of that.
Of my class in particular.
Yes.
Yeah, okay, see, research can tell you. Where do you find that?
There's a website called Gopher Grade, but the
Ah,
website
yeah.
has not been updated for
Ah.
many years.
Okay, okay. Have not been updated for how many years?
I think at least 3 years.
Ah, well, I didn't change that much. But if you do those extra credits, it will bring you to the grade that you want. But it's not about the grades. For me, I don't care about the grades. You care about it. But that's why I give you extra credit. I care about you studying and practicing and learning information, but at the same time, add to your grade because it matters to you. Okay.
The oldest.
Don't say it in a way memorized, it will scare everybody. Try to remember. Try, when you do the exercises, the practice, there is a pattern, and our group, it's not that hard as you think. When you look at the 22, you go, oh, but it's not as hard. There is a pattern. Yeah.
Very big.
You know, okay, what you really need to know, maybe when I ask you to draw the amino acid structure, maybe what you want to focus on, instead of drawing everything, know how many carbons in the arc chain and what is the main group, functional group. So even if you got your H's wrong and your double bond wrong, it doesn't matter. It's just that you know how many carbons and what's the functional group. Yeah, does it get ionized? What kind of interaction it does? That's the important part. So there is an easy way of trying just to draw it very quickly. Yeah. Now, even if you miss the carbon, that's fine. It's not about the carbon chain. It's about, like for lysine, for example, I don't even know how many carbons, but I know that our group is really long and you have an amine group probably in that. Yeah. So 2 weeks for solving that practice set of problems. Okay. All right. So we started talking about the acid-base properties of individual amino acid. We talked about pKa's last time. And we talked about in an amino acid, at least you have 2 pKa's, the carboxyl group pKa and the amine group pKa. And the R group sometimes have a 3rd pKa because of if it has an amine group or if it has a carboxyl group, additional. But we're mostly in the food world, we're working with proteins, not really working with individual amino acids. So we're working with proteins, and then when you have a specific composition of amino acid, you have a set amount of carboxyls and amine. So those carboxyl and amine and their ionization state varies based on the pH, varies between different or among different proteins, and also varies as impacted by pH and also as impacted by ionic strength. We'll talk about salt impact another time. But if we talk about pH, you all have heard of the isoelectric point, right? So the isoelectric point does not mean that the protein does not carry a charge. It does carry a charge. You always have your amine groups and the carboxyl groups that can be ionized, but the net charge is 0. So when you add up the net charge, the negatives and the positives, it will be 0. So the protein doesn't carry net charge. So you will lose the repulsion if you have two protein molecules and there is no charge, no like charge, net negative or net positive. There is no repulsion. So what happens is there are hydrophobic surfaces on the protein. And also there is the plus attracts the minus. Then you would have interaction, protein-protein interaction. And then less interaction with water, and then the protein precipitate. That's why isoelectric point is used to precipitate a protein out of a complex matrix. So now look at the spectrum here of acid to base. So think about it that you have protein in solution and then have the titration, you're titrating. Let's say you are at the isoelectric point of the protein, whatever that is, it varies between different proteins. And then you're adding acid. With that acid, what's in the acid? The main protons, H+. So H+ is going into your solution where you have protein at its isoelectric point. So the pH is going down and the carboxyl groups are gaining protons. So now you are removing the negative charges. So now you start gaining positive charge because your amine group will be positively charged. And your carboxyl group, as you add acid, they will start picking up protons. And by picking up protons, you will start having a net positive charge. So some of you in my lab determine zeta potential. So you determine zeta potential, we usually determine it at 2 pHs, with acidic pH and neutral pH, because if you want to formulate a beverage with proteins, either acidic beverage or a neutral beverage. So when you measure zeta potential at 3.4, your net charge always comes out most of the time. In one case, Saj didn't get that because it's a strange working with pennycress. Don't ask me, it's not a good protein. Okay, so it doesn't follow the norms. Anyway, so yeah, but if you're at the isoelectric point and you start adding base solution, NaOH, let's say, you have OH in there. So OH minus, the OH minus will start pulling protons out of your protein. So as you increase the pH, reluctantly, your amine groups start giving out protons. Usually acid readily gives you the proton, but the base doesn't want to readily give you the proton unless the pH is really high. So as we go up in pH and we are titrating with base, then these guys, the amine group, okay, gives out their protons. So they give out their protons, then the net charge of the protein is negative, right? So always, it's a rule with few annoying exceptions. Above the isoelectric point, you start adding negative charge, net negative charge. And then below the isoelectric point, you start gaining net positive charge. But at any time or any place on the spectra, you will have positive and negative charges. Unless it is very, very extreme pH, you only have positive, or very extreme high pH, you only have negative. Somewhere in the middle will be a combination of positive and negative, but the net will be negative above the isoelectric point, and the net will be positive below the isoelectric. Does that make sense? Okay. Okay. And why is this is not working? Because okay. So let's see what you know, what you remember, what makes sense to you. Hydrophobic properties of amino acid affect the structure of the protein, fat binding properties, and solubility. What do you think? What makes sense to you? Everything? Yeah. Yes. And then we'll spend quite a bit of time explaining how hydrophobic properties impact the structure of the protein. And fat binding, yes, because fat will bind to the protein via hydrophobic interaction. And then, of course, more hydrophobicity, lower solubility in general. So what is true out of the following? Read those statements, take a moment. What do you remember from your past lives of food chemistry, organic chemistry, maybe biochemistry? C. C is correct, but is it only C? What, Sarah? Any guesses, Nagoro?
Yeah.
B and C. Disulfide linkage stabilizes tertiary, not secondary. So it's actually A is correct, A and C. So A, I will explain it with images. How does the hydrophobic interaction drive the formation of secondary structures? Very cool. I will show it later. But now remember A and C. So general theory tells you that the hydrophobic residues well, actually, when the protein is formed in a biological cell, okay, so it forms, you have your primary sequence based on your genetic information, but then the protein is in an aqueous environment. So those hydrophobic amino acids, they don't like water. So what they do, so they start to get closer to each other, interacting via hydrophobic interactions, and those hydrophilic amino acids will just be mostly on the outside interacting with water. But this is not all hydrophobic amino acids will be on the inside of the protein, and all hydrophilic amino acids will be on the outside of the protein. It doesn't work. These protein molecules are really big, but most of the hydrophobic amino acid will tend to hide from water and interact. Now, if you have protein with about 30% hydrophobic amino acid composition, like most of plant protein, you will have large or high hydrophobicity on the surface. And that's in our lab, we measure surface hydrophobicity. Why? And we find it, some of you compared whey protein to pea protein and soy protein, and whey protein really low surface hydrophobicity on the surface. That's why it's a very, very soluble protein. Small molecular weight soluble protein. However, those large plant protein molecules have a lot of surface hydrophobicity, and that's what makes them form quaternary structure. We'll talk about quaternary structure later. So they kind of try to form these larger molecules hiding from water. So soy protein, for example, you form hexamer with lignin because it is trying to hide from water. Whereas whey protein exists as a monomer or a dimer, depending on the pH. So that's the role of hydrophobic amino acid. They tend to find each other and hide from water. That's what you want to know here. Now, this is a little bit fact that just to understand how we assess hydrophobicity, you assess hydrophobicity of individual amino acid based on their interaction with organic solvent versus water. And then you calculate their delta H, the change in energy based on interacting with organic solvents versus interacting with water. If they interact with organic solvent more, they will have higher chemical potential interacting with organic solvent and lower chemical potential interacting with water, then the delta G, which is difference in energy, will be positive for hydrophobic and will be negative for hydrophilic, because then hydrophilic will have higher chemical potential interacting with water. So this applies to all amino acids, with the exception of this guy, lysine. The reason it's a polar amino acid because it has this additional amine group here. And in addition to its amine group, I don't know why it's not showing, maybe the image is over that amine group over here, hiding the amine group over here. It's just how I put the images. There is an amine group here, huh? I can't hear you, Sarah. No. Let me see. I just need to move the image. Where is my mouse? Where is it? Do you see it?
Visible.
Oh my God.
No, Martin. In the top Martin.
Ah, there. Ah, why is it doing that? This is annoying, huh? Never mind. This image needs to be moved a little bit so the amine group will show up. I'll fix it and put it on the. Ah, there it is. Yeah, I was talking about lysine. So because it has, now what? Why did it do that? Was it like that before? What? What happened? You have a question? I thought you were gonna solve my problem. What happened? Hmm. Sorry, I'm just like, why did this happen to me? Ah, it's not escaping. Tech support? Anybody?
Me, I guess.
Taylor, help me. What happened? Nothing is responding to anything. Ah, what did you press?
I just went over so the mouse was hovering on this screen,
Ah,
treating it as a second monitor, hit escape.
Oh.
It still has the bar there. Oh, wait.
Ah, what? What is that? Oh,
Well, it's not disappearing.
but
Yeah,
can we go up there and remove more? High floating meeting controls? Okay, but this is not, what is this over there? Oh,
if we,
why, did that ever happen to any of you?
I'm not sure what.
What happened? This showed up, this bar, all of a sudden. Huh?
Full screen.
I think Zoom does that.
Zoom is very young.
But it wasn't a moment ago,
You start with Zoom after, maybe,
but just a moment ago, it wasn't like that.
then when you escape that, I went back and did.
What did I do?
Stop sharing, start sharing again.
Oh, stop sharing. Up.
sorry,
Stop sharing.
sorry, I was messing with some settings, so I tried some.
And maybe make the full screen. Screen two. Okay. And then put it up.
Oh, this one, present.
Present. Yeah,
Oh, all right.
how many smart people do we need in this room? Okay. So what I was saying is, here, although it is polar because it interacts with water, this long chain will make it have higher chemical potential interacting with organic solvents. So only lysine will have a positive hydrophobic, although it's relatively polar amino acid. So that is against the rule, yes.
Why do you use, would it not make more sense to use a non-polar solvent?
Ethanol, well, it's an organic solvent, so you will have protein hydrophobic interactions with it. I don't know why. To be honest.
But would it, ethanol is also polar, right?
Yeah, because if you have really non-polar, maybe the protein will just precipitate instead of you being able to measure chemical potential. I don't know. I don't know who developed it like that.
How do you measure it?
Huh?
How do you measure it?
Concentrate something that actually measure the energy change, the chemical change.
So that, with ethanol minus with water is to measure hydrophobicity.
Yeah,
right?
to get you this delta G.
So would it, I don't know, in my head, the way I'm thinking is, would it not make sense? Because if you use a non-polar solvent, and if you subtract that, would it not tell you how much of it is, only how much is reacting with the polar portion? Does that make sense?
I don't know, based on the method and how they measure chemical potential, maybe other organic solvent doesn't work as well for the reading. If it was too non-polar to measure chemical potential and it's not as, I don't know, I never did it, so. I don't have a clear answer for you. Look it up and tell us. Okay. All right, so again, this is an illustration of why we need to know the R groups, because look how different they are, and each one of them will have different potential for interaction. So we have the reactive groups, like in lysine, you have the amine group as reactive. And we also have carboxyl and the other amine in case it's a terminal amino acid, like the carbox from the carboxy terminus or from the amine terminus, you will have these groups charged, not in a peptide bond if they are at the end of the polypeptide. So then they will interact with water or have other forms of interactions. Then you have the sulfider group, which is, this is cysteine, and that's the sulfider group, SH over here. So this is a very reactive group that takes part in stabilizing the tertiary structure within the protein, and also protein-protein interactions plays an important role in that, in protein-protein interaction. And then we have the phenolic group, so absorb light, UV light. Also, this group is OH, it can be ionizable. And then we have the serine, threonine. So the serine, the hydroxyl group post-translation modification can be phosphorylated. Can be glycosylated. And then we have the thioether. This is the methionine. Then this is the histidine group, imidazole. I'm not going to expect you to memorize that, but it's just showing you those different, guanyl is for arginine, and the carboxyamide is the glutamine. So this is just to illustrate the different functional groups, and later on we will give more examples about the role of these functional groups in the formation of the structure of the protein and the functionality. So all these groups will affect the hydrophilic, hydrophobic properties, ionization state at different pH and salt, interactions with other components in the environment, and then functionality will be impacted as a result. So we will talk about chemical modification towards the end under protein modification, but here just few examples about chemical reactions that could take place that will change structural characteristics. So from here, acetylation, you add acetic anhydride. So this here, this group, C double bond O CH3 is the acidic group. So that reacts with the primary amine, blocking a potentially positive charge. By doing that, eliminating positive charge, you are increasing the potential net negative charge. So you might be able to change how that protein can interact with other components as with water. Adding succinic anhydride, this whole molecule here, succinic anhydride, it has a carboxyl group that can be ionized. So you're actually introducing a potential negative charge. Instead of blocking the positive charge and increasing the net negative charge, you're actually physically increasing the potential negative net charge. Here, thiolation, you are adding a group that has a sulfider group at the end. So now you are inducing potential protein-protein formation of polymers, enhancing the formation of protein methods. So all of these are called chemical reaction or chemical modification that will impact the structure of protein and impact functionality. Now, is this something we do in the US? Is it allowable? No. Chemical modification is not allowable in the US, however, other countries allow it. But it's not about that, it's about what happens to the chemistry of the protein. Which one?
The CH groups.
Yeah, no, the CH group, I'll show you when I'll show you the interactions within the protein. Most of them would be part of either van der Waals interactions or hydrophobic interactions. So here, another form of chemical reaction is important for us from an analysis side of things is, let's say you broke your proteins into amino acids, and then now you want to determine the composition or the content. So you add ninhydrin, it will react with the primary amine, and then it goes into a series of chemical reaction to give you compounds that will absorb light, so that you can quantify individual amino acids. So different amino acid will form compounds that will absorb at different wavelength. Most of them at 570, proline and hydroxyproline is a 4,4. Some of you in my lab are familiar with OPA analysis. So it has two functions. We can use OPA also in determining amino acid composition by the same principle. So you have the amine group in an amino acid reacting with OPA reagent to give you a fluorescence or a compound that fluoresces. And then you would measure fluorescence at a particular wavelength. The idea here, it reacts with primary amine. So it will also react with the primary amine in lysine. Lysine will have two primary amines. So this we can also use to determine degree of hydrolysis in our lab. So because when you break down the protein, you are releasing more free amines. So the interaction with OPA will improve. So you can determine the extent of protein hydrolysis using this, because now you have more amines. It also you use it to determine free amine in our protein. Why is that relevant? It's relevant to address that. Because why? Because we're glycating the protein. Glycation is Maillard-induced glycation. So when the Maillard reaction happens, you are blocking an amine. So for Andres to determine how many amine groups are being blocked, we use OPA and measure the free amine in the original control, and then the free amine after we do the Maillard reaction. Then we will have less amine, and then we get the difference when we determine amine blockage. In that case, we use lysine as a standard, because lysine is the most reactive amino acid in Maillard reaction. So we use that lysine as a standard to react with the OP. So now we use this reagent in so many ways. So first, determine amino acid composition by having all amino acids react with that, and then measuring absorption after we separate using HPLC. We can determine degree of hydrolysis because we have more amine freed when we break the peptide bond, and then we can determine free amine block due to Maillard reaction. It's often used to determine loss of lysine as well for nutritional quality changes, especially in products that are processed high temperature. So yeah, so this will, help you understand if you ever run an OPA assay, what is it doing with you, and how we are getting what we're getting out of it. Another reaction with free amine is, it's less common, but we use a fluorescence compound reacting again with primary amine and measure fluorescence at different wavelengths. So most common is ninhydrin and OPA. We'll get to those recap questions later. Every year I finish at different time. So, are you ready to know the new topic? Do you want to play? Too much information? At the beginning, we decided not to have a break. We still not. Okay, let's not stretch, stand. It's a lot of information. Assimilate.
I looked up why.
Why? Tell me.
So ideally, because the way I was thinking is hydrophobic, they're usually non-polar, right?
Yeah.
So you should use the completely non-polar solvent.
Yeah.
And then subtract the polar part of it.
Yeah.
But basically what you said is right.
So mother is always right. Yeah, okay.
Although ethanol has the OH group.
Yeah.
if you use a completely non-polar solvent, the protein's not gonna stop
Interact.
soluble at all.
Yeah.
And you need a very solubility, I guess, so.
To measure very well. Yeah, so my intuition, although I never did this test, is good. I like to be confirmed correct. If I was wrong, never tell me honestly. Tell me. Good. Thank you for looking it up. All right, any other questions, comments? Fine, but great. I didn't want to look me up on that book. Huh?
You can look it up.
Yeah, look it up, Kevin.
Some
What
other
did they say about,
professors that have,
huh?
some other professors have much, lower average grades. Some will start with like a O or something.
Is it, that's all what it tells you, the average grade?
Yeah, it
That's
tells you like the
professor
grade distribution.
It's
So, like-
only for grade distribution.
There's another website that has personalized reviews.
Yeah.
You have very high score.
I have a good school. Why do I not know about these things?
We don't know.
You never had to look it up.
I never had to look it
Yeah,
up.
I saw people who in the class, they need to look it up.
So where do you get the personal score?
You're curious. Great professor.
Rate my professors?
You have high score.
So I don't?
It's not right, it'll find you.
I mean,
Yeah.
it's super cool, like
You're
people
wrong.
like rate on a scale from 1 to 10 or 1 to 5, like, I guess, like difficulty, like, I guess, like amount of word. I don't know, other factors, so that can take your score.
Yeah, what professor here?
What's that?
You're not there.
Maybe rate my professor only if you dislike your professor, you go in and make them.
You can have like this, professor or really bad professor.
On that, yeah.
No ratings.
You found me, but there were no rating?
I think this website is not good anymore.
Oh. Okay.
There's no
You
information.
started something, I'm telling you. Now I'm gonna be looking at myself on every possible website.
I see other professors, I think. They have really bad skill. Yeah.
I don't want to know. I don't have.
I used to use the friend.
Yeah.
What's that? Okay, don't tell me.
It's good for like if a class has like 10 professors you choose from, you can pick the best one.
Ah, I
Or you can read like why people recommend or not like.
see. So it's mostly for big classes, like chemistry
Yeah.
classes.
I mean, with this, you don't have a choice, you just have to take whatever professors teach.
Okay. Yeah.
Are you worried about that?
I'm just curious. I didn't know that you can find every grade on. But this is new.
Apparently it's public, like the university releases all the grades.
But without obviously.
Yeah, without the students' names, it
Yeah,
just says like
that's
there's
that's
five.
the distribution. Okay. All right, let's keep going then. Now we're going to move into talking about the formation of the protein structure. Again, this is all refresher, but what I'm trying to do in this class is, although this information is seen before, I'm linking it to, actual testing of structure of the protein and functionality. So bring it to reality rather than just learning about it for no connection. So, of course, as you know, that we have the primary sequence where it's just the linear sequence of your amino acids. And this is really dictated by the genetic coding. So what amino acid comes after what and how long that peptide is. So that's genetic coding controlled by the biological cells. But once the polypeptide is formed, there's a lot, this is gonna bring you probably anxiety. If when I say free energy, Who likes the concept of entropy, changing energy? Okay. Well, I'll put it in the context of protein that will make sense to you, at least make sense to me. So when the polypeptide is formed, those, the theory of stretching and bending bonds, they're always in constant motion. So that creates a lot of free energy, the stretching and bending of bonds, because of electrons, in space. They're always moving and they're always changing. So you have a lot of that happening, chaos, a lot of entropy, a lot of chaos, a lot of free energy. So then what happens is to reach a stable state, so you need to contain the stretching and bending of the bonds. So instead of having them freely rotating, the bonds rotating, stretching, bending, they start forming interactions, bonds, with other amino acids in the chain to contain the energy. So that's entropy, the energy contained. So you have the entropy as a result of chaos, a lot of the energy, a lot of movement, a lot of bending, a lot of stretching, and then you have the containment of that through forming intramolecular bonds. Huh? Free energy. It's not positive or negative. You have a lot of free energy. The delta, when it is in the most stable state, the delta T is positive. When it becomes negative, you get spontaneous evaporation. I'm not sure. Okay, so you start forming these bonds, and then you get to the secondary structure of the protein. So you contain some of this energy, but it's not enough. You still didn't reach the full stable state. And those secondary structures, depending on the protein, you have different beta sheet. These arrows are beta sheet. You have these turns, beta turns, and then you have the helixes, alpha helixes, and those that don't have a particular configuration, we call them random coil. Okay, but still, we still have free energy. We're not done. So then we form the tertiary structure where the protein folds more on itself and forming additional bonding, including disulfide linkages that contains the most energy. The bond of disulfide is a covalent bond, so it contains a lot of that free energy, and then your enthalpy grows, become bigger. The change in enthalpy will become positive from not a lot of enthalpy to a lot of contained enthalpy. So now your entropy is decreasing, the chaos is decreasing. You don't have as much bond stretching, bending, rotation, because now they are constrained in bonds. And then the protein can reach a very stable tertiary structure. Like beta-lactoglobulin, for example, can be happily monomer stable tertiary structure. But those darn plant proteins, they have a lot of surface hydrophobicity. So they're not going to be not liking activists. There's a lot of hydrophobicity. So there's a lot of energy to contain via hydrophobic interactions and other potentially disulfide linkages. Then you get to quaternary structure. But in what animal protein had also quaternary structure? Can you think of one protein from animal source? Oh, yeah, that's true, but something that we work with all the time. Not with casein. So casein is also quaternary structure. Why? Because you have a lot of hydrophobicity. You also have those phosphate groups that can form calcium phosphate bridges, and they can just form a stable micelle. We'll talk about that more. So you have that quaternary structure to also provide stability of that protein, reduce more of that free energy, and also the dislike of water in the case of a lot of hydrophobicity. So that is the transition. The idea is to get to the most stable existence of that protein. Okay, question? Yes, Sarah?
So the protein was a quaternary structure.
Not every protein.
Yeah, but then it has it, that means it has very much of little, it's not.
So, yeah, so casein, for example, beta casein is very hydrophobic, very amphiphilic. So if it exists alone, it won't be solid. But what happened with the casein is special, it's a very special protein. What happens, you have all the beta, alpha S1s and alpha S2 associate, and then on the most of the surface of that micelle is kappa casein with that hair-like glycomacropeptide that stabilizes the whole micelle. That's why the milk, you don't have sedimentation. Your casein doesn't flow out of solution. It forms this very stable colloidal system. It's not a full solution. Yeah. So definitely quaternary structure happens because of a lot of hydrophobicity and a lot of intermolecular interaction. Okay, so this is an amino acid, right? So the amine group to the carboxyl group is one amino acid. Here in the middle is your chiral carbon. So chiral carbon, I will always refer to it as chiral carbon to help us visualize the peptide bond. So the chiral carbon, again, it is the carbon that has different groups attached to it. Only glycine doesn't have a chiral carbon because it has two hydrogens attached to it. All right, so if we follow the chiral carbon, you have this amino acid from the amine group to the carboxyl group, and then you have your peptide bond, which is the peptide bond between a carboxyl group from one amino acid to the amine group of the next amino acid. So it is, the peptide bond is a CN bond. It's not a CC bond, and it is not a NN bond. So it is a carboxyl group to an amine. We call this N-terminus, we call this C-terminus, because every peptide or polypeptide have the N-terminus, the left L, and the C-terminal D. That's the native structure of your protein. So, like I said, primary sequence is controlled by genetic coding. So the genetic coding dictates the sequence and dictate the number of amino acid in each, the type of amino acid, and then the number of amino acids in each polypeptide. So, and with that, since we have all of these differences, we have 22 amino acids, so the combination is, I don't even know how many combinations we can get. So the combination of which amino acid comes what, how many of each amino acid, and how long is the polypeptide, the sky is the limit. So you get your primary sequence, and then because of that primary sequence dictates structure formation, then it dictates functionality. So it all starts with the coding of that protein. So, and of course, essential amino acid is dictated by the primary sequence. So this is again talking a little bit about the peptide bond. It's a condensation reaction. So when a peptide bond is formed, you lose one molecule of water. Okay? And when you break a peptide bond, you gain a molecule of water. So it's a condensation reaction. The average molecular weight of an amino acid is 135 Dalton, but it's the average. You have the glycine, which is very, very small, and then you have something like arginine, very big. Okay. And then most proteins that we work with, the monomers, they range in the 20,000. That means 20 kilodalton. So usually when it is above 1,000, we start the unit instead of Dalton becomes kilodalton. So 20,000, so 20 kilodalton to 100 kilodalton. But there are exceptions. Whey protein size is 18 kilodalton. Alpha lactalbumin is 14 kilodalton. So there are exceptions of proteins that are functional that are less than the 20 kilodalton. And of course, we have other proteins, albumin proteins, enzymes, enzyme inhibitors. They could be also very small, 10, 12 kilodalton. But the majority of the proteins are in this range. Of course, when they form quaternary structure, for example, soy glycine has a molecular weight of 350 to 400 kilodalton because it formed a quaternary structure that is huge. So imagine that protein compared to your 18 kilodalton beta-lactoglobulin, tiny protein. And that should tell you a lot about the solubility. Okay. All right, I said it, but let's see. You remember what I just said a minute ago? Linear sequence and length determines.
Size.
It determines what? Size. It does determine the size, but other than the size, structure, the configuration. So you will hear me say configuration, conformation, that all means similar thing when we are describing the structure of the protein. Is it going to form a globular protein? Is it going to form an open structure protein like casein is open structure, beta-lactoglobulin is globular. And then you have the fibrous protein, I call it. So depending on the composition, you can either form a globular protein, open structure protein, or fibrous protein. Now, I'm just going to talk briefly. I don't want you to stress over it so much, but I mentioned it before. This is the peptide bond. This is the angle of the peptide bond. We call it omega. And this angle is constant and not flexible at all. So you don't have bending, stretching, flexibility, rotation. You don't. Why? Because it is a partial double bond. So this electronegative nitrogen and this electronegative oxygen cannot take the electrons from each other. And when the oxygen grabs the electron from the nitrogen, this becomes a double bond and this nitrogen gains a plus. When it gives it back, then this has the double bond and this doesn't and loses the positive. So it keeps going. It's not a constant situation. The electrons are constantly moving. So that's why this double bond has very limited flexibility. Double bonds, usually you don't have that rotation. So the omega, which is the peptide, omega angle of the peptide bond, has zero rotational freedom, no rotation. Okay, so why do you care? I'll tell you, because we care about two other situations where we have some rotation. Okay. So this is C alpha. So that means this is a chiral carbon. This is another chiral carbon. So you have here two amino acids. This is the carboxyl group. So this is the oxygen of the carboxyl group. This is the R group. And this is this is your amine. This is your hydrogen. Okay. White is hydrogen. Blue is amine. Green is your R group. And this gray red is your carboxyl group. Okay, so we already talked about the omega, non-flexible. And then you have the phi, phi tau sigma, phi. This is phi. And you know what this is called? This is a symbol for. Do anybody know? I keep forgetting, but I reminded myself earlier. Psi. Or psi. PSI. Anyway, I don't know why they gave them those names, omega 5 psi, I don't know why. It rhymes. Okay, so these two angles, this one is the chiral carbon to the amine, is the phi. So, and then the chiral carbon to the carboxyl group is the psi. So theoretically, they have rotational freedom, 360 degrees rotational freedom. That's theoretically. But there's this guy, the R group. We have something called steric hindrance that comes from the R group. You have functional groups, you have your CH group. So it hinders the rotation. The bigger, the bulkier the R group, the less rotation you have. So I expect you're gonna tell me, why do I care? You care because those dictates the formation of the secondary structure and the tertiary structure based on the freedom of rotation. Now, this example here with glycine, with H, you have maximum rotational freedom because there's minimal static hindrance with this little H group. So theoretically, you have that 360 degrees rotation. And however, I already answered this question is because of the bulkiness will determine the rotational freedom. All right. And then I think I also talked about rotational freedom affecting the folding and the formation of the secondary and tertiary structure. Now, another exception where you have zero rotation freedom for phi is the proline, because your amine group is not only covalently linked to the chiral carbon, it's covalently linked to your R group, to the C of your R group. So you have covalent bond here, covalent bond here. Goodbye, rotational freedom. And because of that, what do we call proline? It has, secondary structure break. It has a bad reputation. It's a secondary structure breaker. Caseins has about 17% proline concentration. That's a very high proline concentration, and that's why casein protein has minimal secondary structure, very minimal secondary structure. Secondary beta sheet.
How about the beta?
Beta, well, you can form beta sheet and beta turn. You can form them, but it's very minimal. It depends on where those prolines are located. Whenever there's a proline, it's going to break. Maybe you get beta turn because the beta turn is a turn rather than its structure beta sheet like that. Yeah. So you have minimal secondary structure when you have that high of a proline, and this is because of that rotational freedom that you don't have in proline. You don't have that flexibility to bend, orientate, and make interactions to form your alpha helix, your beta sheet, which we'll talk about. So peptide backbone is a series of, from here, the chiral carbon here, to the other chiral carbon, and everything in between is called a peptide backbone. It's not very important to anything we're going to talk about later, so I'm not going to expect you to remember the backbone, okay? But it's just things they teach us, but this is not relevant to what I want to talk about in this class. I don't expect you to know, but I do want you to know that this omega, not necessarily remember the 6 degree, but remember that you have zero rotational freedom. And these other two, you have theoretically 360, but it depends on the R group. And that dictates how the protein folds, rotates, forms secondary and tertiary structures. Okay. The other very trivial information that is just part of learning about peptide bonds that I don't expect you to remember, but the peptide bond exists in trans instead of cis because of potentially the R groups of steric hindrance. So the amino acids rotate in a way that they can naturally exist with minimal steric hindrance, so minimal interference of the R group. So you'll see an R group here, an R group here, up, down, trans. That's it. So this is the not natural cis. And in proline, because of its unique R group, it can exist in both cis and trans. That's all, but it's not, again, it's not an important information to anything later on, but it's part of learning the chemistry of the peptide bonds. Okay. I tried. Here's another bribe for grades. I offer it all the time, every time. So whenever I have an old figure that I cannot find a better replacement, or I don't know how to use ChemDraw, I give you an option. Draw me this in ChemDraw with the same colors of that red to see the changes during hydrolysis of peptide bond. And get close to. The prettier it is, I have changed from +2 to +4. Now that I know I'm graded online, maybe +10.
Put a review for you.
Huh?
And the best professor ever.
Yes, that
+10.
+20s. Don't take the exam.
So some of us is not student, so what you gonna get?
Chocolate. Yeah, so do look at my worst images and make them better and get something in return. If you are a student, you get a grade. If you're not a student, you get a chocolate. Do that work. I don't have time to do this, but I realize that this is very shabby looking, ugly, but it tells the story. The story that I want to tell here is you can break peptide bond. It's not like it's formed valence and cannot be broken. So of course we can break it. We have to break it, especially in this example when we're doing amino acid analysis, compositional analysis, we have to break the peptide bond, all of it, so that we can release free amino acids. And the way we do it is strong, concentrated HCl. 6 normal, sometimes depending on the method, we can even use 12 normal, but it gets diluted a little bit. And we do have a microwave digestion unit, so it's not really 24 hours at 100 degrees, can speed up the digestion. But anyway, what happens with this high acidity or high alkalinity is your peptide bond is broken in the presence of water. You get your amino acid, and the OH goes with the carboxyl group, and the H goes to the amino group from the water molecule. That's why the red is important, if you draw this for you, to follow. Huh? This OH,
Yeah.
it comes from the water.
Okay.
It gains, yeah. So when you break it in the presence of acid and heat, that bond breaks. In the presence of water, the water has hydroxyl and hydronium ions, right? So the water molecules are dissociated, basically. It's not existing as H2O. So the OH from the water goes to the carboxyl group and forms a bond. And then the hydrogen from the water forms a bond with the nitrogen. So it picks up 1 molecule. Every peptide broken will pick up 1 molecule of water. And every peptide formed regenerates 1 molecule. Okay, so acid hydrolysis is usually commonly used for amino acid composition, but those of you that have done amino acid composition know that tryptophan gets degraded. You cannot determine tryptophan in acid hydrolysis. So every time we need amino acid composition, We have to do acid hydrolysis and we have to do base, alkaline hydrolysis. So the alkaline hydrolysis is used to determine tryptophan. Acid hydrolysis also degrade partially and or fully cysteine and methionine. So there is a third way of digestion to prevent the oxidation of cysteine and methionine. Every time it's a cane, those of you in my lab know that in the acid composition analysis of the cane, you have to digest the sample 3 different ways and run them on the HPLC 3 different times. Interesting to get the rest. Yeah.
Why don't you use base? Can you just use base?
The base will degrade, destroy other amino acids. Yeah, so it is not, yeah, so they're not perfect. One of them cannot do one without destroying some of those amino acids. And on top of that, when you do the acid hydrolysis, you can never quantitate actual glutamine and asparagine because these both get converted to glutamic acid and aspartic acid and are determined as glutamic acid and aspartic acid. The only way to know how many glutamines you have is by I asked you if you looked up the glutamine
Sequence.
sequence. Yeah, how do we get the actual glutamine? Yeah, how do we determine if we're doing that by proteomics? So you get the sequence based on the genetic coding. And also if you do DNA coding, you know which component of DNA gives you what amino acid. Yeah, that's the only way to do that. To get the sequence through either DNA analysis or proteomics. But doing amino acid composition, you have to do that 3 different digestions. Again, this is another opportunity for making this look better. All right, so this is basically the peptide bond can also be broken by enzymes. And we'll have a whole unit on enzymes and how they operate. But different enzymes, proteases that cut peptide bond, have different specificity. So you probably learned that somewhere else in life. But trypsin, for example, is a very specific enzyme. And that's why it's used in proteomics, in mass spectrometry, because it always, you know where it cuts. So you know the potential peptides generated. If you know the sequence of your protein, and if you do trypsin hydrolysis, you know exactly what peptides are going to be generated. So it's used a lot in a proteome. So it really cuts after the carboxyl group of lysine or arginine. So it cuts the peptide bond here after the carboxyl group of lysine or arginine. That's very, very highly specific. Now, a very not specific protease is pepsin. Doesn't have, it cuts many, many places in the peptide bond. That's why pepsin is a digestive protein and we have it in our gut. So, yeah. And another thing I want you to learn about proteases, there are endoproteases and there are exoproteases. Like there are in like starch hydrolysis, amylases are endo, glucoamylases are exo. So same situation here with endoproteases, they are gonna cut in the middle of the peptide. Whereas exoproteases, they take 1 amino acid or 2 amino acids at a time from the extremity, from either N-terminus or C-terminus, depending on the enzyme. So we have endoproteases and exoproteases. It's important to know this because later when I give you examples, I'll be talking about endo and exoproteases. All right, question? Are you thinking how you're gonna make this better for me? Look at it, it's just really long. I probably got this table from like Xeroxing book. Yeah. Why are you laughing at me? Nicole? It still gives you the same idea. All right. Okay, now to the fun stuff. Free energy, enthalpy, entropy, the change in energy, all of that to help us understand the folding process of the protein. So we start with primary. We talked about the concept of the free energy. You have a lot of energy, a lot of big rotation happening, stretching, bending, a lot of energy. That's not a stable state. So the protein needs to find stable state. So it starts forming bonds and forming your alpha helix, beta sheet, even random coil, beta term. You start containing some of that free energy. Still not enough. You still have free energy. It gets contained by further interactions and stabilization with disulfide linkages, for example, hydrophobic interaction, ionic interaction, stabilizers. And then potentially forming quaternary structure, depending on the hydrophobicity and the sulfide groups in the protein, or even like in the case of casein, potassium phosphate interactions. All right, so as we go from here to here, from primary to secondary to tertiary to quaternary, we are containing the free energy. We are trying to reduce the entropy and increase enthalpy. So the containment in energy. So the steric strains we talked about is due to your R group. So the R group in the sequence will determine whether we can form alpha helix, whether we can form beta sheet, whether it's impossible to form either. So it's very important, the impact of steric hindrance. So it's a combination of steric hindrance and free energy that will lead you to the formation of the further structure of the protein. So that's exactly what I'm talking here about steric hindrance, the restriction based on your R group, that green thing, your R group, the stretching and bending and the rotation, all that free energy, and then reaching a stable form by folding. And that's your favorite equation in the whole wide world. And you need to remember. But just remember it in simple terms. So delta H is your enthalpy. So it's the when you contain the energy, the change in that, the change in the amount of energy contained. So that's enthalpy, delta H. Delta S is your entropy. In other words, your chaos. When your bonds are broken, you form chaos. You release free energy. So that's why denaturation, you would get negative delta G, because you're increasing the chaos at a particular temperature. And therefore, the delta H also is decreasing because you're losing containment of energy. So when delta G is negative, spontaneous denaturation. Okay. Anybody want me to repeat this here? You good? You good? So now we had this original question, how does hydrophobicity impact formation of secondary structure? Well, it's the main driver of the formation of secondary structure. Why? Because what happens is the same diagram that I showed you, where a tendency of hydrophobic residues to interact with each other brings that chart of the folding. So they want to hide from water and they want to start interacting with each other. So they come closer, they fold on each other. But what happens when they do that, instead of interacting with water, they start forming hydrogen bonds when they are in close proximity. So hydrogen bonds is electronegative atom, like oxygen, interacting with a hydrogen that is attached or bonded to an electronegative atom. It can be an N, for example, not just an O here. Okay, so, and water is pushed up. So you form hydrogen bonding among the residues, and then water goes to the outside. That's how the secondary structure is stabilized by hydrogen bonding. So hydrophobic interactions brought us to the proximity where hydrogen bonding can take place instead of water with the residues, and the water goes out. So this is the role of hydrophobicity in the formation of the first step of folding, which is our secondary structure. So secondary structure is stabilized by hydrogen bond. And speaking of bonds, so this is a perfect illustration of the different types of bonds that can happen within a protein molecule, within the polypeptides to reach a stable state. So a lot of different bonds take place, or bonding types of bonding, to reach to the most stable state. The first one, which is the weakest bond, is dipole interaction, or we call it bonding. So it happens between two neutral functional groups. So these are neutral, that means there's no, like, the carries charge. So it is weak but additive. So a lot of van der Waals interaction or dipole-dipole interaction takes place. So at the end, you can contain a lot of energy because it's additive. Although the individual bond is weak, contains low amount of energy, but it is additive and important in the stabilization. The other one that is important is hydrogen bonding, and we said electronegative atom bonded to a hydrogen. The hydrogen forms hydrogen bonding with another electronegative atom. So you will find a lot of hydrogen bonding in forms, in secondary structure forms like alpha helix, beta sheet. These amino acids, threonine, serine, aspartic acid, and glutamic acid, forms the most hydrogen bonding. The other one that is strong is electrostatic or ionic. So if you say ionic bonding is fine, if you say electrostatic bonding is fine. So positive and negative, basically, charged, oppositely charged groups. And it can occur among different groups, mostly amine and carboxyl, but depending on the pH, these two groups, cysteine and tyrosine, can be negatively charged and can take part in ionic impact at different points. So ionic interactions can be repulsive or attractive. So depending on the charges of the groups, either they repel each other if they are alike, or interact with each other if they're opposite. And those are the groups that usually are charged: arginine, histidine, lysine, aspartic acid, glutamic. So they are the ones that are mostly forming those type of interaction, with the exception of cysteine and tyrosine at high pH. Hydrophobic interaction is a very strong bond as well, and also adds to the stabilization. Well, it starts the interaction, starts the folding, but also takes part in additional folding of the protein. Okay, and it is mostly among non-polar groups, obviously. The last one, which contains the most energy because it's covalent, is disulfide linkages. So of course, it occurs between two cysteine to form cysteine. Cysteines to form cysteine. Okay, so cysteine is the double bond, is the two sulfhydryl groups interacting, two cysteine will form cysteine. So, and the covalent linkage only between sulfide groups, other than the peptide bonds, of course, and the other original bonds in the amino acid. So it adds to the stabilization of the tertiary structure, contains a lot of free energy, adds to the enthalpy and reduces entropy. This is an important table. It's very important because you need to know later on when we talk about changes during processing or during analysis, you want to know that covalent bonds are the strongest bond, contains a lot of energy. This is kg per mole, contains that much energy per mole. It happens between cysteines, and then you can disrupt it by reducing rate. So those of you that run SDS page under reducing, you add beta-methoxyethanol ethanol. Sometimes we use BTT in different assays to also break sulfide groups. So these are reducing agents. Hydrogen bond, it's an important concept to know that hydrogen bonds can be enhanced by cooling and can be disrupted by heating and other detergents. So urea and detergents can break the hydrogen bonds. That's why when we do SDS page, you add your Lundy buffer has SDS. So what SDS does is breaks the non-covalent impact, including hydrogen bonds, including hydrophobic interactions. So your protein migrates differently. It's individual proteins in case they form hydrophobic interaction or hydrogen bonding. So urea also is used a lot in a urea page or in 2D electrophoresis to disrupt also those hydrogen bonds. Have you ever formed a gel with gelatin or cement in like with science or whatever to form? You take the collagen, you heat it, and then the miniatures, mostly your hydrogen bonds are broken, you get this random structure. But then when you cool it, hydrogen bonds form again and it will become a gel. So it's a reversible process. So you heat, you cool, you get it out. Yeah, just because hydrogen bonding break and then upon cooling they form again, and then you form that gel. Okay, and then you have electrostatic. So it's the second most containing of energy. So you have covalent, then electrostatic contain a lot of energy, followed by hydrogen bond, by hydrophobic, and the least is the van der Waals or dipole interactions. So the electrostatic, of course, they are disrupted by salt or pH. Anything that will impact the charge will disrupt, either cause repulsion or cause more attraction. Hydrophobic interaction, detergent, organic solvents because now the hydrophobic residues that are hiding from water, if you put them in organic solvent, they will unfold and then they will interact with the organic solvent. So that's causing disruption of hydrophobic interactions. Heating can strengthen hydrophobic interactions and cooling can weaken hydrophobic interactions. And we'll give examples about beta-casein, the heating and cooling in milk and the movement of beta-casein from the non-cell into whey. We'll give you that example that reminds you the hydrophobic interactions. So actually cooling kind of weakens it, but heating strengthens it. So from this slide, what I want you to remember that chaos can happen with breaking just only few bonds. As soon as you do something in the environment of the protein that causes a couple of hydrogen bonds, for example, to break, That's all you need to get to denaturation. I think when I posted, this was G, but it should be H in your slides. Make sure it is the summation of all the enthalpy in the bonds. So when delta S increases tremendously, it increases just with breakage of a little bit of bonds. 1 to 3 bonds will cause a tremendous increase in chaos. Then this becomes bigger than the contained energy, then delta G becomes negative, and that's spontaneously important. Okay. So sometimes we have to have conformational adaptation. So for example, if we want to have an enzymatic reaction, sometimes if you're running a kit, it tells you it has to be at this pH at an optimum. Also, sometimes it tells you need to have NaCl. Why? Because you're changing the charge where the enzyme is going to bind or be able to bind. So sometimes the protein change in conformation to allow certain reaction to happen. And you can change that by changing the environment. So you can influence that conformational change by changing the environment. And that's all what it's saying here. Sometimes you need stability, sometimes you really need conformational changes. So when you need stability, disulfide bonds come in handy. To induce disulfide bonds, so for example, you want your gel to be stable, right? So you want to heat to a certain temperature where you can induce denaturation and then allow proteins to come together with hydrophobic interaction. Then they become in close proximity to each other. If one has sulfide group and another has sulfide group, then disulfide release can occur and you stabilize your gel. So sometimes you need to stabilize a certain structure and sometimes you need to make a change to promote a certain reaction. Okay, this will make sense later. So these are just basic concepts, but I'm giving you a little bit of example where this will make sense later on when we talk about structure, function, and different food systems. All right. Perfect timing. Next time we'll start here. All right. Thank you.